Hey, thanks very much, and you're being a little too kind. I really appreciate you inviting me to speak. By all means, if you have questions, chime in the chat or speak. I'm cool either way. I don't mind being interrupted. Let's just start with that, okay? So if you have some concepts, I will go through this as concisely as I can, but I have a tendency to ramble, so I apologize in advance, okay? So I just want to call that out. Just as a call out, the reason I'm showing you this stuff is not so much because I want to brag, but it's also just to provide you some context of the historical context I'm coming from. So prior to joining Databricks, I was over at Microsoft. I actually helped build what is now known as HD Insight. I was on the 9-person Project Isotope team that had basically went up to Microsoft management and said, hey, we need a big data system, so we're going to embrace an open source Linux-based product. That's okay, right? And so that was a very rough conversation, but that's what it was. And that was when I was part of the SQL Server team. I've been with SQL Server on the engineering side since SQL Server 2005, and I actually had been working with SQL Server since 6.5. So it's been a while. I also had helped build some of the distributed systems over at Bing, the search engine. Yes, I realize the search engine sort of sucks, but you know, it is what it is. And Azure Cosmos DB, I was also on that team because I wanted to do a nice round approach in terms of the one thing I hadn't really dived into was key value store. So there you go. Boom, I decided to do that too. So through this stuff, I also happen to be a senior director of data science engineering at SAP Concur. Because we were trying to build up the data science and data science engineering brain trust at Concur as well. So that's a little bit about myself. I did want to say, if you are interested in learning more about Learning Spark, because in fact, we're actually not going to talk about Spark that much during today's session. I mean, I'll bring it up, but that's not the real purpose of today's session. But you can get the book for free, Learning Spark. Just go to dbricks.co/get-ebook here. The book's completely free. I'm happy to be one of the co-authors of the book as well. So that's why I figured I'd call that out, okay? In terms of what my company is, Databricks. And so this is my one and only marketing slide, so don't worry, I'm not gonna dive too much into it. The key thing that you guys care about basically is this part. We're a company with more than 5,000 customers and 450 partners worldwide, and we're also the original creators of popular data machine learning projects, not only Apache Spark, but also Delta Lake, MLflow, and Koalas. Okay, so the context is we are the founders of the company, and a bunch of us that are with the company. And I'm not a founder, but I was an early part of the company. We all come from the data space, and we recognize a lot of the problems within that data space, and that's why we figured to help build a company like Databricks to address all those problems. And so in a lot of ways, this session that we're talking about today, Bring Software Engineering Practices, is actually that. It's how do we provide some rigor and process? Because I'm sure in the courses that you're taking, not just this one, but any course, right? There's the concept of software engineering practice. And what usually happens more times than not is that it's called a process. Like there's a process that you have to follow, like a checklist at minimum, a JIRA item, whatever. There's a process that you have to follow, so that way there is a form of rigor. What I'm going to talk a little bit about today is that, at least in the past, you're going to laugh or cry, depending on your perspective, on what this rigor was, okay? Because this rigor basically didn't exist, all right? So to provide you also a little context, because I also want to be cognizant of all of your time, I'm going to try to do this in about an hour, 15 and 30 minutes, okay? Just so that way there's plenty of time for questions. This is actually an abridged version of the Coursera course, Bringing Software Engineering and Practices to Data and AI, actually, okay? And so it's a course that's coming out, I believe, in mid to end of January, but it's actually combining, it's actually 4 of them. One's called Reliable Data Infrastructure Fundamentals. One's called The Complexities of Distributed Systems Data Processing, Data Engineering Best Practices, and Machine Learning Lifecycle. So, sorry, there's a little typo there, but those are the 4 courses that make up the specialization. That this is an abridged version of it that hopefully you will enjoy, okay? All right, so, oh, sorry, there we go. All right, so I'm gonna talk a little bit more on the why reliable data infrastructure fundamentals, okay? I'm gonna harp on this a little bit, not because I'm OCD, though that's true, I am OCD. It's more a matter of the question, what does data reliability have to do with software engineering practices, right? You're going like, okay, wait, your title brings software engineering practices, and the first thing you dive into is data reliability. What are you talking about, right? So I want to address that right from the get-go, to provide some context here, right? And what it has to do is it's about the state of your data. It's a vague term, but as you dive in more into it, you're going to understand. And state's not just about your data. It's about the configuration of your system. It's about the metadata. It's about all these other components that are required in order to maintain your data, so that way it's reliable and trustworthy. We're going to get into a little bit about what I mean by reliable and trustworthy a little bit, but the context is that the systems that you typically are working with, for example, when it comes to databases, they typically have ACID transactions, i.e., they protect the data so that way when you insert the data or update or delete the data in a database, the whole purpose of the system is to ensure that the data doesn't get corrupted. That you know what you put in, you know what you read is exactly what you read. In the case that we're dealing with right now, because we're talking about distributed systems, the underlying cloud object stores themselves don't actually have reliability. Yes, they replicate the data to 3 or more locations, whether you're talking about Hadoop or Google Cloud Storage or Azure Data Lake Storage or Amazon AWS S3 or whatever it is you're talking about. But the state of that data is actually not reliable if you place it under pressure. So in other words, if I'm putting a single file into S3, you're probably right. I probably don't have to worry about it that much. If I'm inserting thousands of files, small files into S3 at any one time, and I'm just picking on S3, but this is applicable to almost any cloud object store, there's no guarantees that the data that you wrote in there actually is exactly the way it was supposed to be, right? This is why, for example, when you download some software, especially open source software, would tell you, hey, here's a checksum. You need to check that the file you just downloaded matches the checksum to make sure it's completely correct, right? That's an oversimplification of the problem, but that's the context, right? All of these things come into play with the state of your data. So let me be very specific in my example. Okay, well, let's talk about source control instead. Not so much about data, but state of your code first. Okay, so when you use GitHub as this example, right? You keep track of which versions of the code you have. You allow for multiple people to read and write that code at the same time. You roll back to previous versions, right? In other words, when you realize you screwed up, and I've done that many times. So my GitHub has lots of rollbacks, right? You explain and comment why are the changes. You get feedback, say, hey, I'm going to make this change, like, update my Gitman to HTTP. Somebody comments saying, hey, dude, that doesn't make a lot of sense because of XYZ. That's fine, right? So you call that out. That's the state of your code. So that's a standard oversimplification, but a standard software engineering practice that I have the ability to contain that state. And so I'm going to naturally ask them, how do we do this for our data? Right? And if you really think about it, yes, maybe databases do some of these things, but the reality is databases don't do these things. Not all these things. In fact, I think a few slides later, I go into that. But that's the whole point. We do all this versioning, controlling, and process and rigor on our code, but we don't do any of this for our data, or we don't. At least if we do it very poorly. And this is a call out to all of our systems. Okay, and then before I even dive into that, then I get into this concept of microservices monoliths. Don't worry, I'll get back to the state in a second. But the point is, when you look at these systems, right, especially the older relational database systems of the past, these are what they term as monolithic architectures, right? They basically, it's one central point for the database to query. So everybody queries the database, everybody makes an insertion to the database, update, delete. If the database goes down, your entire business system goes down with it. So then you do all of these things to keep the database up and running. You do active clustering, you do backups, you do 20 million other things to keep the system up and running. But it's one central point of failure. It's simple because now I have only one system to access. But as you put more load onto it, as you ask more people try to access it, when more people try to change it, that monolithic architecture starts falling apart. Okay, so that's an important concept, right? And that's what databases systems are. Okay, they basically are monolithic architectures. I go into this a little bit later, but the change, and for example, a lot of you folks, since you're coming from college right now, right? You're more used to the microservices approach of the world, and trust me, it's great. There's a lot of pluses to this. Okay, it's designed for scale. It's designed for distribution. It's designed for high concurrency. It's designed for two pizza boxes, teams, small teams, managing, maintaining all this stuff. It's awesome. There's a whole bunch of other problems that go with it, though. Okay. And so if you get nothing else from today's session, in other words, if you decide that you want to leave in a minute because you're bored with me talking, the one thing that I will always tell people, learn when it comes to software rigor, that it's not one or the other. It's just simply picking the right tool for the job and actually having some rigor behind it. That's it. Okay. If I was to summarize this entire course, all four courses in terms of specializing, is that choose the right tool for the job and have some rigor behind it. All right. But the reality is, like I said, implementing what I just said is significantly harder. Saying it's easy, implementing it, that's a whole other problem. And so let me start with V1, the database engineering lifecycle. If I'm sure many of you are looking at me going all weird, like, what do you mean database engineering lifecycle? Like, that doesn't make a lot of sense. You're a software engineer and you use a database, and that's good. Your perspective is correct, by the way. But in the past, that's actually not what we did. We actually basically made the database the center of everything, to the point where it got a little ridiculous. We would do things like, because I want faster performance, I would put all the business logic I ever had into stored procedures and put those stored procedures, because the stored procedures were right next to the database, it would actually be compiled and run faster. But that meant literally the database wasn't just the central point of logic for your data, it was the central logic for your business logic too. So talk about rigor, it didn't exist. Like, it was like you just threw store procedures, anybody could go and access it. Sure, you did security and authentication, authorization, all that fun stuff, but the reality is, no, there was no real rigor. For example, I love showing this one. Hopefully there's no copyright laws on this one, but basically it's like people literally would look and say, forget about SQL Server for a second, they would just say, hey, Excel, I just put everything in Excel. Excel is a database. It has everything I possibly need. And for the individual person, obviously that could probably even work, right? But as soon as I have the statement, like, I want to share this information with multiple people, okay, I'll give credence. Now there's Office 365, it makes it a little easier to share. By the way, between Office 365 and Google Sheets, I'd rather use Google Sheets anyways, but irrelevant of that little call out. The reality is, if you're running an Excel spreadsheet on your desktop and that becomes your database, you've got a whole bunch of problems when it comes to scaling and distribution. For you personally, that's perfectly fine. For you to run a business, not such a good idea. All right, and that's more or less the call out, okay, from this little thing. And so now I'm going to elucidate or elaborate a little bit over that traditional monolithic approach to data, right? The database is in the middle. You've got the business applications, you got your users here, right? All applications and clients would center around this single database. That's all they would do. They would just, everything was on that. Like I said, store procedures, business logic, everything was inside here. It is a central point of failure. All data and state, version control is in that database. And of course, that meant anytime you try to distribute or scale out, this became massively complicated, right? So if anybody who's ever built a sharded relational database system, yes, you have the simplicity of having familiar management tools to do such a thing. But the maintenance overhead of running your own database by yourself, like sharded database system, is beyond complicated. Network cables, network latency, putting them on the wrong rack. For example, even something as simple as running your own Hadoop cluster, if you don't do it correctly, you're actually going to do a DDoS, the equivalent of a DDoS attack onto your own network. I still remember when I first joined Concur, this is like one of my little funny stories. We at the time, it was a large, right now it's tiny to me, but like at that time, it was a large 40 node cluster, right? And I was telling our IT infrastructure guys, like, hey, no, you need to put this on your own rack. Like, it has to be own rack, own routers, own everything. And they're like, no, it's okay. We've got really fast routers. And I'm like, no, you don't understand. And so they went in and did it. And so all I did, like, seriously, it was just a simple TerraSum, TerraSort, like one of those like generic, like the hello world of Hadoop. Like it wasn't anything typically terribly complicated. I go and run that, and basically I saturated the network to the point where basically I took half of Concur offline for that one job. Because basically I did the equivalent of a DDoS attack to the entire network. Because Hadoop distributed systems are really, really chatty. Okay? And so that's the thing about microservices in general. They're super, super chatty. So because they're chatty, they basically saturate the living daylights out of your network. All right? And so because they saturate, bam, that it collapses. So I go into this a little bit later on how we had to change the entire cloud infrastructure because of this one simple concept. Okay, and all of cloud had to change just because of the chattiness of microservices. We had to build what's basically known as network mesh grid networks or flat storage. The point being, when you have an application that talks to your storage layer, there actually only needs to be one hop. If you have more than one hop, you're basically doing a DDoS attack to your own system. So yeah, I've got more stories, but if you have time, I'll tell you them. But right now, I still have other stuff I want to tell you, okay? So if I translate this back, what is the state of your data? So, and again, this is not a full list. This is just a overly simplistic version of this, about of tracking state, okay? The state of your data. All right, how do you keep track of which versions? Okay, well, you can do processing the schema code in separate SQL files, and you can version control that with GitHub. So that part's relatively simplistic. But how do you version control your data in a database? All right, well, you can do full, incremental, change backups, and or change history tables, all right? So this now becomes really, really hard to maintain. And later on, when I talk about the AWS story, the real quick call out basically is, and I'm just getting ahead of the curve, but to give you some context, what it became obvious to us who are in the data space, especially when it comes to scale, distribution, cloud, and all these other things, it was no longer writing the code that was hard, it was maintaining any of these systems. That's actually what was difficult, right? And so, for example, just maintaining states of your data, that became a pain. Of how do you structure that? How do you save that? How do you do all of these other things? The IT couldn't keep up. The actual operations became harder. That's why you hear the term DevOps, right? Because it required the developers to actually understand the underlying operations of the system. Before, the database guy would just say, here it is. And then the operations DBA would just say, okay, I'll buy the biggest, largest machine that I could possibly get with the most memory, with SSDs. Actually, at the time I was doing it, we didn't even have SSDs, was brand new too. So we would short stroke all these spin disks so that way we could go ahead and get faster performance. We partitioned the database across all these different disks so that way we could handle random IOPS. And dear God, I'm going to go off on a tangent, so let me stop now. But the point is, like, it was a massively painful process. And so then when we went into microservices, we recognized, okay, we need to get the smart people, the developers, to actually understand the implications of their memory, the implications of how they were using CPU, the implications of how they were using network, right? They had to, and how they were using disk. They actually had to understand these things. So that's where you hear the term DevOps originally. But don't worry, DevOps also is just as a nebulous term as big data or AI these days. In other words, everybody has their own interpretation of what that means. So for me, I'm just going to scale it back to say, okay, is there an actual software engineering practice behind it? If there isn't, I don't really care what you call it. There needs to be a software engineering practice first. Okay. All right. So there's just that one example where that already was painful. How about allowing multiple people to read and write your data? Now, Databases were well designed for this process. So that's great. And in production, you can even like, they did silly things on security, but that's fine. You could definitely do it. And CRUD operations are protected due to asset operation protections. CRUD, sorry, is create, replace, update, delete. Basically, if you look at SQL statements like insert, update, delete, merge, that's what we mean by CRUD operations. How do you manipulate the data, okay, of your database? So those first 3 points, actually, databases were super well designed. There is a sharding, partitioning, distribution problem from the standpoint of that when you actually had to handle higher concurrency load or higher throughput loads than what a single database could do, right? Typically, the solution is distribution. So databases weren't designed very well for that, but if you sharded or do other things, maybe you could get away with that. But tracking all of this stuff often required separate logging and separate authentication systems. And if you're familiar with how the cloud works today, you'll notice that right from the get-go, that's built in, right? The whole reason you have cloud and you have to understand AAD on Azure or Google Identity or AWS IAMs. It's all about building authentication right from the get-go, authorization, tracking, logging who did what. All of these systems are already in place. Now, they're not great, I'll be fair, let's be completely fair, but they build it right from the get-go, so that way you're able to start tracking and figuring out what's going on. These database systems were often, it was done after the fact. So in other words, you would it was easy to hack the system to basically skip or lose things, right? And so that's one of the things that databases weren't really very good at doing. I'm sure some of them have improved it, but for all intents and purposes, it's not like the ubiquity of cloud systems right now. Okay. Now, rolling back to previous, that part sucks. Like there's no more. Okay. Basically, it required you to go take an old tape backup, restore it. Or maybe if you're talking about AWS Glacier, you can restore from older disks. But the point is that you often had to go back in time, manually get a disk or manually get something to restore that data. It was a pain. That's why AWS and actually all three cloud providers, actually all of the cloud providers, including the ones in China, right? They all are very good at providing database services now. So you can just click on something and you can restore it. So on a single database, that's actually not bad in all seriousness. But if you have to do it in a distributed manner, again, this becomes beyond painful, right? The maintenance cost of finding it, figuring out which one actually went offline, how to restore it, bring that back up, make sure that they all match metadata versioning wise to everything. That in itself is painful. And then even if I accepted that fact, first of all, the first version, keep track of which versions is already painful. There is no concept of commenting. If you look into like software, like in terms of the software and database business, data business, like you'll hear things like metadata management versus master data management. Most of them suck. If they are decent, it's because they're specialized to a specific thing, like a small subset of the business problem. There's no real such thing as Git comments for data versioning. That doesn't exist. Even for small data, this is not very well done. Okay, like to put it rather bluntly, and I apologize to any of you who, any of you have worked on SharePoint, but I'm just going to insult it. The whole reason why SharePoint even exists right now was because they were trying. It was the basis of tracking data, and that was just for small data, and it's a grotesquely system. Like I could go on for hours about the engineering behind it. It's ridiculous. Okay, but it's a real problem. So that's why SharePoint exists. Okay. Now, for all of you who are doing it now, you're like, what's SharePoint? Okay, think of it like Wiki, but for Microsoft. In other words, not very good. Okay, so that's more or less the context. Now, again, I might bash Microsoft a little bit, but just only because I'm a former employee. Okay, but it's not because the Microsoft employees were bad. Let's be very clear. So now let me be nice a little bit. Okay, right? It's because the problem itself actually is a hard problem, and people didn't have processes around any of this. That's why. It's not because Microsoft said, I want to build you a crappy product. It's because us who were working with data, whether it was like Excel spreadsheets or custom lists or putting data into a database, we didn't think much about, like, was there an engineering practice around it? We just thought that, oh, okay, we're just going to shove the data in there and everything magically works. Because in some ways, that's what a database was. It was just, it magically protected the data. But the problem is that it's more complicated than that, right? There's a lot more to this than just those concepts. So that's the reason why this became convoluted, because people realized, okay, wait, I'm trying to solve actually 20 different problems at once, and I shouldn't have been trying to do that, right? That's ultimately the reason why that happened, right? And then now that's just for small data. For big data, streaming data, this concept basically doesn't exist at all, right? Because we're just trying to bring in and ingest the data as fast as we possibly can, and we're not even trying to make sense of it, which is horrible. All right, so ultimately the problems of these monolithic architectures is code complexity and maintainability. Deployment becomes a bottleneck. There's a fear to change. There's a lack of ownership. Because you have really large groups that are trying to do all these good things, to try to develop these complex systems, as opposed to like looking at the problem as a bunch of small little problems put together. And this will become a little bit more apparent when I talk about microservices in a second. Okay, there's this concept of failure dependencies. There's a concept, absolutely, one size does not fit all, because the idea is that up to the point we're trying to chuck everything into relational database. We try to make the relational database solve all of our problems, but it didn't. And it was beyond painful to scale out. All right, so now that's the problems of monolithic architectures. Don't worry, I'll go back to later on where I say, actually, there's some good things about it, by the way. Okay, but let me talk about microservices first. Okay, so when we started making that shift to microservices, a lot of the push, it's not like microservices is relatively new. You're going to hear the concepts like SOA and all these, and DevOps and all these, CI/CD. They all came out roughly at the same time. It came out at the same time as we also started doing base, and instead of doing ACID for like to protect your data, for atomicity, consistency, isolation, and durability, to protect your data, we went into base, the concept of basic, available, steady state, eventually consistent. That timed with distribution, scale, time with cloud, all came roughly at the same time. So all three of these concepts actually influenced each other, and that's actually what resulted in microservices. Okay, and so back to this the slide again. And by the way, you guys can get access to the slides, no problem at all. I'll definitely send them to you. There are links to the original sources for this, so it's not just me that you're going to hear this from. You're going to hear from like other people in the industry as well. So I made sure to include the links here, right? The whole characteristics of microservices is that you often hear like Amazon say, I want 2 pizza box teams, right? I want basically only about 8 to 10 people, 2 pizza boxes in a single team. So it allowed for smoother communication. It allowed for decentralization. It allowed them to work independently of each other. You allow them to do only that one thing. They focused on one thing and only that one thing really well. And the left bone point, you build it, you run it. That's that DevOps mentality. So now that you build it, you're going to get paid that night. If it breaks, it's not some DBA, some IT guy or gal that's got to take care of this. You're going to go ahead and make it. So you're now incentivized to actually write good code, because you don't want to be paid till 2 in the morning to go fix it, right? So that's a really good thing, by the way. That's what I love about microservices, okay? Here's your problem, okay? This is a real diagram, by the way, guys, okay? It comes from the slide deck here, a view of Amazon by its microservices. This is a diagram of the N thousands of microservices that make up Amazon.com, okay? So do you think that this is remotely possible for you as a single developer to remotely understand what this stuff is? Like, it's not possible, right? And that's actually the brilliance of microservices. You don't need a single person to understand the whole infrastructure. In monolithic architecture, you typically had an architect that understood every single component of every single thing end to end, right? In the microservices world, you can't afford to do that, because that's the only way you scale. You let other people take charge. There is this concept of contracts. No, not legal. I mean, actually, in some ways it is legal, but the idea is that you give me a JSON input, I will give you this output. I will guarantee you this latency. In other words, I will get it to you this fast. I will guarantee you X number of transactions per second, right? That's the context. right, of microservices. All right, I tell you, I give you this, you give me that, and you tell me what the threshold of what you can supply. Right, that's the concept of microservices, and this allowed individual teams to go do their thing. So I already talked about two pizza box teams, so I'm going to skip that. Oh, actually, I did want to call it one small quick thing. The two pizza box teams actually is not a new concept. It's actually well embedded within the military, and I don't mean the U.S. military. I mean any military organization, because there's research after research, whether it's from the U.S., from Europe, from Asia, it doesn't matter. They all came to the same conclusion. When you have a chain of command, when it comes to running a military team of any type, each leader can only handle somewhere between 5 to 8 personnel. That's it. They can there's only going to be a smooth communication between 5 to 8 people, and that's it. Okay. If you go beyond 8, you actually want to split it. You would actually rather split it into 2 teams of 4 than actually have 9. Now, in reality, that's not always possible, but that's the concept, right? You would actually rather do that because you want smooth communication. That's actually the whole concept of this 2 pizza box teams. It's actually a very well known in any military organization, whether it's, your Army, Navy, or even search and rescue, because that's actually where I learned it from, by the way, as being part of the search and rescue teams. I learned that long before I ever learned the 2 pizza box teams, because we were saying, when we went out and did a search and rescue, the maximum we had, in our case, our number was our organization, our number was 6 actually. The maximum was 6 per team, but that's the concept behind it. Okay, so this is a well-known psychological, sociological thing. So this is not specific to software engineering, but it's very applicable to this day and age. So I'm going to skip through this because I think most of you know this concept really well. But here's the microservices approach, right? Instead of actually trying to build a single one software, one application, what we're doing is we're building multiple services, like a recommendation service, a messaging service, alert service, display ad service, catalog, document store service, cloud object store service, a message store service. Don't worry, I'm going to get into why. Okay, so if I look at an e-commerce example, the recommendation service is recommending new purchases to visitors. The messaging service allows you to talk to those buyers and sellers. Display ad service, notification of price drops, new items. Same as the alert service. You have a catalog service, which basically contains the product SKUs. All of these things are required for a simplistic e-commerce, okay, online company, okay. So from a data perspective, let's say we're going to use a message store service. Well, if I need to have the alert service and messaging service, they're going to need a message store service, okay. From the aspect of these 2 services, the messaging alert, they don't care if the messaging sort service is Kafka, File Store, HBase, Cassandra, whatever you want to throw in there, okay? They don't care about that. They just care that I have an API, a REST API that I'm supposed to hit. I give you my request, and you're going to give me a guaranteed return of X latency with X transactions per second. That's all they care about. So that means whoever runs that message store service, they can swap it out with whatever they want, okay? And that's exactly what happened, by the way, okay? I'm alluding to something very closely, so just hold that in mind, but the idea that we could just swap things out, okay? If I want a cataloging service to basically hold all the product SKUs of climbing equipment. I'm a climber too, so let's just do that. All the climbing equipment I want to buy, we have a catalog service for it. So maybe a document store service, or maybe it's a database. Doesn't matter. The point is, it's a service. I send an API call from the catalog service, and I'm given a guaranteed for transactions, a guaranteed for throughput, a guaranteed for safety of the data. That's all I care about. Provided you give me those guarantees, then we're good to go, right? Recommendations, a machine learning service. Okay, it needs to talk to the cloud object store service. Okay, if I want to do a display ad service, the display ad service not only needs to access the cloud object store to get the images for the display ads that you see on the website, right? It also want to talk to the catalog service to figure out, hey, what items can I display, right? I want to display this particular Trek bike, right, or this particular carabiner, or whatever it is you want to go do. But then it also wants to do recommendations. So it'll just hit the recommendation service to get that information. Whether it's the user, she or he, going ahead and getting the recommendation because they searched for it explicitly, or because the display ad shows it, as they're doing a search on the side, honestly, doesn't really matter. They just need a service that actually provides the information. So what ends up happening here is that you end up having individual teams that maintain each one of these services. They build a really good recommendation, a really good messaging service, a really good alert service. They maintain that. They maintain that not just for this e-commerce example, but they can maintain this for multiple things, right? Multiple teams, not just in the organization, but maybe even multiple teams outside too, right? That's the whole point of building services, okay? And then the key thing, which I alluded to right from the beginning about database systems, right? There's a massive separation of business logic from the data. The business logic is in the applications themselves, these services here. The data is actually in the message store service or the cloud store or the document store service or whatever else. And we can swap in and out, and it's gorgeous. I love it because now I don't, it's a black box to me. If I'm building a catalog service and I can trust a document store service to take care of this for me, I don't have to think about it. This is wonderful. Okay, what's the problem? All right, let's skip to that. Okay, actually, you know what? Before I talk about what's wrong, let's just go through this real quick, right? Because of this, what's great about it, okay, you can keep track of which versions, so you can employ better software rigor because there's smaller teams, but each is maintained and operated pseudo-independently. Each may or may not do the task well, and I'm going to talk to you about what a real big problem is on this one when it comes to taking stack of your data, okay? When it comes to these microservices, because the problem is your data is not in one place now. Your data is in multiple services. You may not even know where it is now because you were just using a service, right? It may be sitting somewhere in Timbuktu for all you know, right? You don't know. It's a black box. That's a problem now. Sorry. You want to allow multiple people to go right and oh, sorry. This is what I didn't mean to show this. So here's the problem, and this is from 2016. Okay, this is only from 4 years ago. Okay, I called out in the bottom of where I snagged the image from, but this is like an example of all the different database, just the actual database and applications around data. Okay, don't worry, you don't have to. I'll send it to you so that way you don't have to like take a picture of this because this is insane. But the point is that can you maintain all of this? Right, you can't. Right, it's ridiculous. So that's the problem with the microservices system now, right? In a nutshell, like we built so many specific systems to solve specific problems that now we have so many different services and solutions. You have no idea which one's which, and often you have to mess with them until you finally figure out which one's actually useful or not, right? And so that's why it's so painful. And then, you know, okay, how about allowing multiple people to read and write your data? Yes, super well designed for this purpose. There are key issues around CAP theorem. I didn't talk too much about that in this session just because I already have too much as it is. But the context is that when you build a relational database system, when you talk about CAP, it's consistency, availability, and partition tolerance. It's the old thing, you can only get to pick two, right? You don't get to have all three. There's no, anybody that markets to you that, oh, we solve all three of the things that CAP is basically lying to you. Okay, we've tried so many ways to solve that problem. We have not solved that problem. There are systems that are getting close to it, sure, but there's always deficiencies, always. Okay, and so whenever you look at it, you have to be aware of that. So long story short, when it comes to traditional database systems, typically they solve C and A really well, consistency and availability. If you're looking at like availability and partition tolerance, that's typically, for example, like your NoSQL store, like your Cassandra, for example. Or if you're looking at consistency and partition tolerance, that was something like HBase, okay? What that means is that basically if it has to choose between keeping the system up and running and having your data consistent, it will choose to keep the data consistent even if the data isn't available, even at the risk of making it not available. And vice versa. Like if you choose something like Cassandra, it's basically well designed for availability and partition tolerance, but it means that your data may actually not be consistent, okay? And so but the thing, of course, is that I'm not saying that's a bad thing. The thing about microservices and what it introduced was us realizing not all data required consistency and availability at the same time. There are plenty of sets of data that only need a consistency and partition tolerance. There's plenty that only need availability and partition tolerance. For example, if you're doing likes on your Facebook, right? You want it to be consistent. In other words, if I clicked like, the like actually came through. You want to make sure it came. It might not be available. In other words, if that person's profile is on a node that happens to go offline, okay, well, you just don't see that particular message temporarily until the message comes online. So it's not crucial for it to be available, but it's crucial for it to be consistent, right? So that's one small example, but that's what I mean by like, not all data requires both consistency and availability. So it's actually possible to do this. The problem, as per the previous slide, is that it involves multiple microservices, and then you only have a limited team. Your team can't know everything. So your team can't go ahead and maintain Cassandra and HBase and Spark and Hadoop and, right? They can't do that, right? It makes it simpler with the cloud, sure, where we can spin up an HBase service or we can spin up a SQL service, and that's all true. But the thing is that you still have to understand, as a DevOps person now, understand the underlying consistency issues, availability issues, partition tolerance issues. What's the pros, what's the cons? You're still going to need to understand all that. And so cloud may have made it a little bit simpler because the cloud vendors provide these services to make it easier for you to maintain, but it doesn't change the fact you have to understand how the stuff works, which means you don't want to have too many of these systems running concurrently. Rolling back to previous service is easily the hardest because it depends on which service. And remember, it's black box. So you might not know how they're keeping any of the data back. So if the service itself, the document store service that happens to use MongoDB, let's just say, right, itself says, oh, you can roll back by doing this. That's great. But often, more times than not, these systems are not designed for that. So then you have to create your own service on top of MongoDB to allow for rollback, which means you have to allow for versioning of data, which is its own set of complexity. So you have a team that's designed to do it. That's great. But I don't think everybody wants to learn how to do that. All right. And same problem with explaining comments and why you get changes and get feedback, because don't forget, if I go back and look at that Amazon view of services, how do you track the metadata on that? You don't. It's not happening. There's no data lineage here, right? You can try, but it's not going to exist, right? So the thing about monolithic architectures, ironically, is that they're actually well designed for this idea of metadata, master data management for data lineage. It's just that when they built it originally, they didn't think about it. So this is what I mean by, it's not actually bad to have a monolithic architecture, just provided you know when you're using it, right? And provided there's a good reason, i.e. I need to have data lineage. Okay, then having a pseudo monolithic infrastructure actually makes sense, right? That a pseudo monolithic infrastructure doesn't mean you can't have it based on microservices. Look at Hadoop, look at Spark. For all intents and purposes, these are microservices running off of cloud object stores, but then it's a monolith from the standpoint that I only need to run this one query and it auto distributes everything for me. But what's happening underneath the covers? We're running a bunch of REST API calls too. Remember, these systems were like, remember I was giving that story about Hadoop basically crashing, doing a DDoS attack on my network. It's because it's super chatty. Why is it super chatty? Because we're doing a lot of little bytes, bits, transactions back and forth. So super chatty, I'm doing a DDoS attack on my own system right now, right? So that's the telltale sign of a microservices system, right? But Hadoop as a whole is a monolithic architecture. Spark as a whole is a monolithic architecture because I only need to run query, right? I run one Spark SQL query, I run Spark submit, bam. All of that microservices stuff that's happening underneath the covers is hidden from you. You don't have to worry about it, right? So that's an example of where I'm saying, hey, we got the best of both worlds, because you as the user don't have to worry about, did I run this on node 1, 5, and 6, right? You don't care. Did it run? That's all I care. Did the query come back faster? Yeah, that's all I care about. The people who created Spark, the people who create these distributed systems, we're the ones that figure out how to distribute, how to scale, how to do all this stuff. And for all intents and purposes, it's a black box. Whether we stored it on DBFS, stored in S3, stored it on Google Cloud Storage, stored it on Azure, honestly, you don't care, right? because all you care is that I get a query back. So that's the context of monolithic. It's not so much monolithic versus microservices, is knowing when to use what. All right, so this is, I'm going to speed through because I think I'm running a little later than I expected here. But Netflix has a great blog. I just tossed in a little note for the Netflix logo, but that presents the principles of chaos engineering. Okay, it's a great blog to give you some context behind all of this. And in a lot of ways, everything you're learning about data right now these days, that's actually, it's based off of what Netflix did, okay? And the long story short is that basically is the dream of scale up linearity. I add more nodes, I go faster, okay? You try to do that with a database, it never works. It just doesn't work, period. From a software engineering perspective, it's because the compute engine itself and the storage semantics are too interlaced, they're too tied together. When you decide that you want to scale up scale out your storage, you don't have any mechanism outside of sharding to scale out the compute engine, which then that's where your problem is. Because if you ever build distributed systems, you have to build them with distribution in mind, which basically means the separation of the storage layer from the compute layer. So for example, when you look at Spark, that's exactly what it is. Spark, people say, oh, it's a great storage and compute layer. Like, no, it's not. It's a great compute layer. It has no clue what the storage is doing. It doesn't know, it doesn't care, right? There's basically code that says, okay, if you're gonna hit Azure Blob Storage or S3 or Hadoop or whatever else to figure that out, but what is it? It's a bunch of REST, for all intents and purposes, a bunch of REST API calls to access the storage. That's all this is. It doesn't know, it doesn't care, right? That's the right way of distribution. You actually have to have a separation. That way you can scale your storage and you can scale your compute independently of each other. All right. And so the reason Netflix had to do this is because they were basically, with their Oracle database, approaching the traffic limits. They basically were breaking Oracle for all intents and purposes. If they needed to make changes to the schema of their database to give people more reviews or whatever else, it required downtime just to update the schema, so that way we can add more favorites, or you can add a new feature, UX feature, so that you can use Netflix. There's a couple of links inside here, again, or we'll hand you the slides so you can review it. But basically, they need to do it because they also no longer wanted a single point of failure, right? That's what it boiled down to for them, all right? And so there's a couple of blog posts. I'm going to go a little bit more into the 5 lessons we've learned using AWS at the tail end. But these are 2 very important concepts behind this entire concept of why Netflix needed to create failure. So what's a very important software engineering practice is this idea that you don't make the assumption, whatever you're building, especially when it comes to data, that it's always going to work. When we built database systems, when we built applications that were relying on the database systems, we shouldn't have, by the way, but we did make the assumption that it was always going to work. Either because the DBA maintained it, because the database was well built, because we put enough InfiniBand connections on the back end, all these different things. We had a SAN, a network attached storage, whatever else, to ensure that the database was always up and running. It was 99.999, always running, always running. We never had to worry about it, okay? Where Netflix realizes that because you're talking about the cloud, and especially at the time they were doing it, it was even buggier, nothing ever worked consistently. So instead, your approach to software engineering is you always make the assumption it will break. You don't always make the assumption things work. Always make the assumption things break. That's why you hear people talk about test-driven development or pair development. For example, when it comes like the versions of different agile development cycles. I'm not going to tell you which one to choose because they all have the pros and cons, and that's actually its own gigantic can of worms that I'm not going to don't want to get into right now. But the context is the reason we have paired development, the reason we have test-driven development, the reason we have these things is all based on this simple premise. We have to assume the thing breaks first. We have to, as developers, as engineers, go out of our way to try to break whatever code we create. That's the key concept that you want to learn from this one. And then we're going to get into some specifics behind it shortly. But like I said, the quote there, the best way to avoid failure is to fail constantly. That's absolutely the right approach to the problem, okay? And so here's the high level principles of chaos engineering. Okay, um, you're basically forcing yourself to constantly experiment on your distributed systems. For example, what I mean by experiment, Netflix in the early days actually would, and this is what Chaos Monkey is, what I was referring to here, okay, would actually go out of their way to break the connection between my iPad and Netflix and see if I could still watch the movie. Early on, you probably don't no longer going through this, but early on, I would, because I was also one of the earlier Netflix users too, tells you how old I am. I would get emails and alerts saying, hey, how was your movie? Or how was your show? And the reason they did that, people were thinking, oh, because they cared. No, they didn't care. I mean, they do, but it wasn't because they're being nice. It's because they actually went out of their way to basically kill the connection. So did I lose connectivity when the connection was killed? They will purposely break the connection to me. Now, it's because their application would say, okay, well, I've cached enough of the movie, so my app, once I lost connection, my app will reconnect and then reconnect to go ahead and get the stream again. And meanwhile, because I've cached enough of the movie, I should be okay. And so more times than not, sometimes what you'll see, for example, when you're watching a Netflix movie, it's working perfectly fine in 1080p or 4K or whatever it is that you're currently working. All of a sudden, it'll start pixelating. It'll go down to 640. And then it'll go back to 1080p and or 4K or whatever you're doing. Why is that happening? Because it reverted to the cache, or it ran out of cache, and so it actually lowered the bandwidth of the movie to transmit more of the movie to you faster, so you wouldn't lose connectivity until it could make it up for it. That's actually what's happening behind the scenes. Okay, so this is what I mean. They just assumed the network was going to crash on them. So they built in systems to prevent that from actually preventing you from a user experience perspective. Was it better to have high quality 4K the entire time? Or was it better to have but then have interrupts? Or is it better to have 4K as much as you can, cache as much as you can, but then pixelate downgrade your stream until you can catch up? And obviously, in the case of Netflix and every other streaming service, that's what they do now. Okay. And so that's what I mean by the principles of chaos engineering. I'll have you read it later because, like I said, I'm already running a little longer than I meant to. So I apologize for the rambling. But that's a really real concept, real world concept of what I mean by chaos engineering. Okay. And so when they built all these systems with their chaos engineering, right? It's like I said, the first point, chaos engineering worked for teams and coaches to focus on building their own teams using those principles, the principles I just previously alluded to but skipped over. But what happens that most businesses can't afford to do this, right? Netflix could afford to do this, but most companies can't actually afford to do this. So they actually built this concept of hybrid systems, okay? So they extend existing monolithic architectures, and then they built many services. Now, problem with that statement that I just said, and that's why it's bright red, is even though I just told you Spark was all in some ways monolithic architecture, but also using microservices, the problem is that most of these hybrid systems that were built was not that. It wasn't about them knowing when to use monoliths versus knowing when to use microservices. It was, I have a monolith, I have a product, and I'm just going to call it a service. And that's it. So they still built it in the same way as they built a product. So they still had 9, 12, 18 month delivery times. So it's like, okay, so in other words, the whole purpose of building services is that you have a small team to deliver agile, to deliver quickly. They can deliver something in 3 months and then update it every 2 weeks or every week or every day, whatever. But the point is that's what you're trying to do, right? Monolithic architectures, especially when it comes to database systems, what we did was basically like, okay, here's the functional specification. Here's the design. We're going to review it because it's perfect, because everybody knows exactly what they want from the beginning. Please note, I'm being very sarcastic right now, okay? Then I have 12 months to go build it. And then after the 12 months build it, I'll do a beta test for 6 months. And then you will love it. I'll allude to I'm going to jump to that really shortly. That's not even close to reality, okay? In reality, more time what happened was that nobody read the functional spec. They built it. By the time it was 12 months from now, whatever they were trying to build was no longer needed. Or the specification of it changed so much that for all intents and purposes, whatever they built was worthless. That's actually what they built. So think about it this way. So you're saying, oh yeah, I'm going to build a bunch of services all in 12 months from now. Cool. So you all build a bunch of services. They haven't talked to each other because they're all working in silos. 12 months later, they've all built these services that convey to the functional spec, except nobody bothered updating the functional spec. So when team 1 is saying, hey, I expected this, team 2 is like, oh yeah, we changed that 4 months ago. So by the time they all built their stuff, they had multiple services that were really just products that they still didn't understand how it worked, and they never knew how to talk to each other. So building one of these was already bad enough. Building multiple of these basically became a failure. So later on, by the way, how I end today's session, I'm actually talking about culture. I know that sounds a little odd, but it's actually an important concept, because the people you bring in, the thinking that's involved is actually ultimately what actually has to be done. And I'm going to talk a little bit more of that, but it's actually this is a super important concept when you talk about software engineering practices, because a database person is not well suited to become a microservices person unless they're given time to learn to make that change. Right? A microservices person, like I'll be simple, even simpler. If you know C++ really well and you want to switch to Java, right? It's not like this can happen tomorrow, right? You're going to need to give that person time to understand the context and how, because the C++ person, they're so like, but I love the memory. I love memory management. I love memcopy. I love all this stuff. What is this? Yes, right? They hate the JVM. Like, dear God, the way JVM does memory management is insanely stupid, okay? And it's not because JVM was a bad idea, by the way. It's just because they were trying to make sure it could run on Linux and Apple and, you know, and Windows really well. So basically, when you build something that's designed really well to run on multiple systems, it's not really good at anything, right? That's usually what ends up happening, right? And ultimately, that's why we build distributed systems, because we compensate for the fact that if we just throw more hardware at it, we don't have to care, right? That's how we compensate for stuff. We just throw more hardware, distribute it, and we magically solve the problem. But then ultimately, that's the problem, right? Then your people that were really good at one type of programming language or one type of thinking or one type of development cycle, making them do that shift is really, really hard. And that's why I'm calling out that culture aspect of things, okay? And so that's what I mean by that build hybrid systems. Like, the people who built them didn't understand what it meant to build services. Since they didn't understand what it actually really meant to build services, they just basically did a version of their original design, which basically is the worst of both worlds, okay? So, and at the same time as they're doing this, remember, this is where the big data space comes in. And you've probably seen a version of this where we talk about the 3 V's, where big data is about volume, velocity, and variety, right? You have lots of changes to your data. A lot of the data is coming in faster, and you have a lot more of that data. And big data, the key context behind big data, because it's an overused buzzword, is the simple statement of saying, you have to build a system that can handle 2 or more of these problems at any one point in time. You can always purpose-build a system that handles velocity well. You can always build a purpose-built system that handles variety well, and you can always build a purpose-built system for volume really well. What you don't have is actually a system that can actually handle all 3 of these really well, okay? So that's the concept of big data from 3 V's. The problem, going back to initially why I was talking about data reliability, is actually, it's not really the 3 V's, it's actually the 4 V's. Right, the missing V is data veracity or data reliability. So back to the original statement. Why do I say that? Because when we design monolithic architectures around databases, what we were good at doing is knowing exactly what the schema of the data was, what we're going to use the data for, because it was expensive to hold a database, to put stuff into a database, and we actually cared about what data went in there. We wouldn't throw garbage in there. We actually had to care about it. We had to know what was going inside that database. When we switched over to big data, we're just saying, give me everything. Like, just take everything and store it all, store it all, store it all. We're going as fast as we can. We're just storing everything. We'll worry about figuring out what data we have later. We just get it stored. Well, that's great in terms of you storing it. And to the storage vendors, that's awesome. But what you're missing now is this entire concept of saying, did you actually need any of the data that you're storing? What you have is noise, not data. Do you actually need any of this stuff? Maybe you do. I'm not going to pretend that it's all bad. That's why, again, why I say sometimes it's microservices, sometimes it's monolithic architectures, right? So I'm not going to claim it's always bad, but we definitely shifted in our going to this, like the big data 3Vs, in our attempt to distribute everything, in our attempt to go to the cloud. We just default to the idea it doesn't matter what the data is, we're just going to store it. Didn't matter if it was corrupt, didn't matter if it made sense, didn't matter if anything else. We just shoved it in there. And so we lost that data reliability in the process, right? The thing that we absolutely had with monolithic architectures, we lost that when we made that shift, okay? And so veracity then requires data reliability, which thus requires ACID. And that's what I just talked about in the beginning, about this idea of atomicity, consistency, isolation, and durability. I'm not going to dive into this too much just because I figured you'd probably reviewed it a little bit, but if you need to know, Wikipedia pages actually have a really good explanation. Or you can take my Coursera MOOC later on. I delve into this a little too much. But the context is that now you're putting protections around your data. If the schema of the data changes, you're going to protect the schema so it doesn't break. If you're doing an insert and an update and a delete at the same time, one of them's going to win out. It'll send a message to the other clients that are trying to do the update and delete, using that as an example, telling them, nope, you failed because you were not allowed doing it, because in this case, the insert took precedence over your update and delete. Retry again, okay? If it's inserting data into two different partitions, you got MVCC or optimistic concurrency controls. So then you're not a big deal, but in all these other cases, yeah, you're gonna have to care about that. So now, this is what I'm saying, like where we're slowly shifting back, right? If monolithic architecture is here, and hopefully you can see my screen, my fingers here, and microservices here, we basically went from here all the way out to here. Now we're slowly coming back in the center because that's actually where we need to be, right? You can be fast, but that doesn't change the fact that I still need software engineering rigor. You can store lots of data, but doesn't change the fact that I still want to know what data I'm storing. You can track state, but you care about all those other concepts. So whatever you're doing when it comes to software engineering, you need to care about these things. You need to care about tracking versions of the data, providing enough feedback, metadata, comments, GitHub, whatever else to let you know what you're doing with that data. If you don't know these things, then what ends up happening is that you're storing a bunch of stuff, you don't even know why you have it. And that's worth less than not even keeping it, because you're sending money to keep it and you don't even know why you have it, okay? All right, and so like I said, that's why the microservices approach works. That's why because you could actually go ahead and do this, right? But you still need this, right? That's ultimately the come down, right? Oh, sorry. So how do you bring veracity liability to this? That's ultimately the question for you guys, right? And so this is where now I'm getting closer to why these projects are failing, and also getting closer to culture, because ultimately when it comes to software engineering practices, that's what it comes down to. In the past, when we talked about databases a lot, 60 to 85% of data warehousing projects failed. All right, they failed. Here's just 3 pointers. It's actually a lot more than this, but I just wanted to provide a little quick context for it. Right, the long project development cycles. It took forever. You would have heard waterfall methods for development. Okay. There was lengthy delivery times from documentation to time to market. Like, you hear acronyms like GTM, go to market, or TTM, time to market. But the point is that it took a long time to build this thing. All right. The business questions or data change, rendering the reports that you generated meaningless, basically. That's why, from a high level, data warehousing projects failed. By the way, I'm sure any of you could tell me, oh, but there's these other 20 reasons, and you're absolutely right. I just wanted to focus on these 3, that's all, okay? So how do microservices address this? Oh yeah, they address them well. Okay, we do agile development instead of waterfall, right? Allows for faster feedback. Perfect. In terms of lengthy delivery time, no. We deliver faster, allow fast delivery of project, better. It's that fail fast mentality. you build it, you get it out. If it fails, you learn from it and you update it and you build something new, or you incrementally update it so it doesn't fail anymore. Perfect. Your business questions, because they change so often, the questions or the data change is meaningless. You adapt it to business questions or to real-time data changes. And that's important because a lot of people, when they built data warehouses, for example, they said, well, the schema is always going to be this way and we're not going to need to change our questions. Except for any successful business, that's exactly the wrong statement. Any successful business, that means they're going to have changes to the schema because they're going to need to take it, they're going to ask new questions and they're going to add in new data sources because of it. So you always have to assume change. Okay, so I told you 60 to 85% of the data warehousing projects failed. So now that microservices, did I fare any better? Anybody want to guess? What was the result? 60 to 85% of the data projects failed. That's all it did. It's same thing, there wasn't any difference. It just went from data warehousing projects failed to data projects failed. That's all it did. You look at the McKinsey reports and all these other things, Gartner reports, they all say the same thing, okay? And so, what had happened is that they failed for different reasons, right? So when you don't look at the model, it's not agile enough, and there's monolithic architectures. That's relatively straightforward. The microservices, remember that big data landscape slide. Too many options. How can you be an expert on all these things? You can't, right? There's a lack of data veracity or reliability. So even if you stored all the data, you didn't know what you had. And you had no way to backtrack to even figure out what it was. You often were missing the data dictionaries that would define it. Even if you had just a JSON document, there was no other document that would tell you, okay, well, what does this actually mean? The column for the column name in year one of this data source versus year two, it can be the same column name, but mean completely different things. And trust me, that happens a lot. This is a very, very common thing to do. They didn't even do simple things like put inside their JSON what version of the JSON is. So you made a REST API, you got the return and you stored it, but you forget, okay, is this the JSON from last year's version schema or this year's schema? Because don't forget, if you make the wrong call, you can still ask for last year's schema from the same REST API. You often, more of the time than not, that's a flag. So if your old code is still there, but you didn't bother saving it or they didn't bother putting anything in the JSON, you don't know which version of this is, right? And so there's a high level, it's not actually a deep dive, but it's a high level blog post, which I included in this area, 5 fixes for your failing big data initiatives, lack of supporting culture, ignoring feedback, overwhelmed data swamps, data silos, too much or too little data. Okay, I'm going to talk right now about the 3, and then the culture thing allows us to talk about the 2. When you switch to microservices, just like you saw with that AWS diagram, what happens that there's no one person that understands how the system works anymore. And so since that doesn't exist, any person on any of the tens or hundreds of pizza box teams that exist, they're just storing the data and they're storing it haphazardly. So this is the concept of overwhelmed data swamps. So you'll hear data swamps, data salad, data bog, whatever. It's all the same thing, okay? It's basically to say the cleanliness of a data lake, except it's all crud. But what it means basically is that you don't know what data you have. That's what it basically means. Data silos basically means this concept of saying, oh, team A is grabbing this, team B is grabbing this data. They're both grabbing the data from the same source. They're storing it in different ways. They actually leverage each other's expertise. They're applying business logic without ever talking to each other. The output of the results are actually different numbers to solve the exact same thing. So now all these individual teams are working together. They're not working together, excuse me. They're actually going ahead and basically just doing their own thing. All right. And I know it sounds funny, but sometimes we have too much data and sometimes we have too little data, right? It's the old Goldilocks rule, right? You have to get it just right, right? Too much data because you've defaulted to say store. I haven't figured out why I even needed this data. Or too little data, which is like, Well, great. You know exactly what data you have. Have you bothered figuring out what else you're missing? Right? And so just from that data perspective, this is what I mean by data veracity or reliability. If you actually have data veracity and reliability, if you have a single data lake, logically, physically, I don't care if you have 1 or 15, but logically, if you have a single data lake that all your data teams are now accessing to access this data, in which we've done so in a reliable manner. So in other words, if there are streams of data coming in, they can all go to a single table. Multiple streams going to a single table, and there's ACID transactions to protect that data. That means your different teams that are accessing this data can actually go ahead and have the same results because they're actually talking, they're going to both hit the same source. Since they're both hitting the same source, provided you've got a workspace or an environment for people to talk to each other, communicate, and whether that's Slack, that's why Salesforce bought them up, or a wiki, or a workspace with Jupyter Notebooks, I don't care. Like, you want to use, heck, that's why Databricks exists, by the way. It's just as a quick context, but I don't care what you do, just think that you actually are talking to each other. By that, allowing for that, then you actually prevent that data silo concept. And how do you talk to each other? It's like every other software engineering project. You have to have rigor. You have to have process. Now, why am I talking about this concept so much? Is because I've alluded to, and in fact, the one thing that I'd love you to take the Coursera MOOC, even if it's just for free, the free. I don't care about the money part. Okay, it's because the extended course, I actually interview a bunch of my friends. Okay. That I've been working in the industry for a long time, from the EVP over at Tableau to a bunch of architects. Okay, but the reason why I like talking about this little perspective is I actually want to talk about specifically a software engineer, one of the CEOs and one of the software engineers. The CEO of a company called At Scale is a guy named Dave Barron. He and I are old friends. We work together. I've got plenty of stories on that, but I'll skip that part. But the reason I like this to tell you the story is because what ended up happening, his quote basically is this: now, after all these years of databases and big data, we're finally seeing a convergence of of data engineering and software engineering. Okay, and so this is the reason why it's titled "Bringing Software Practices to Data and AI." Okay, because up to relatively recently, data engineering was not software engineering. Data engineering at best was scripting application development. And I'm being far too kind when I say that. Okay. Rigor almost was non-existent. And especially from the standpoint of even if I had rigor around my code, there's no rigor on my data. Right. And that's a key thing. I did not have rigor on my data. So wait, if like people talk about data mining or data science is or data is the new oil or data is the new gold or whatever other lovely marketing phrase you want to toss in here, right? It's all true, except for the fact that just like, that's why I like using the word data mining, right? You actually have to mine. In order to get the gold, you actually have to dig. There's a lot of work to get there. Then you have to dust it. Then you have to pour a lot of chemicals to clean it out. Then you finally get the gold, right? There's a whole bunch of steps to get there. Well, when we built big data systems, we only were worried about, okay, just get the data and store it. That's great. But how about the process? How do you take it? What do you keep? What do you save? If you need to keep all of it, where do you save it? How do you recreate the process so that way if you're running a machine learning job and you need to go back to older data so you can make sure your machine learning algorithm still works, how do you even recreate that? You can't, because you have no versions of the data. So that's more or less the context here, right? That we did all of these things, but we never understood how our data worked. We never provide any rigor around it, okay? And so in the end, whatever it is you do, it's about being able to make that choice, right tool, right job, and also figure out how to apply various techniques so you can look at your data, categorize your data, and understand which ones require rigor, which ones don't. You know, if you got 5 million images, it's probably fine just to chuck it in S3 and be done for the day. If you've got financial transactions, you might want to care about that one, right? And so, which then invariably leads to this concept of culture, okay? And so, oh, right, actually, let's see. How am I doing for time, by the way? Because I'm probably running a little longer than I expected. So I probably got another 20 to 30 minutes. Is that still okay, or would you like?
Yeah, that's still okay. That's still okay. Please go ahead.
Okay, cool. Yeah, because the cloud, everybody said, clouds saves everything, and I'm like, and from the standpoint of how I define it here, it absolutely does. Except it made it worse, so much worse. Okay, what's cloud good is because this idea that you're abstracting, decoupling the application from the infrastructure, right? And so you know how I talked about data, when you distribute data, you say compute and storage layer are separated from each other. Same idea for applications, right? The application and the underlying infrastructure runs, you actually abstract those suckers away. The reason you want to abstract is so that way you can swap out the infrastructure with other infrastructure, and provided you're still using the same REST API, it doesn't really matter. You can now standardize everything, and you can automate it. And it relies very heavily on using web services to do such things. So all good stuff, okay? So where did this come from? It came from Amazon, okay? Amazon was the first one to really go do this. I can actually tell you some good stories on Azure too, but I really want to focus on Amazon, okay? And it's because Amazon was growing really fast and IT wasn't keeping up. It's as simple as that. The baseline on how this worked was that. And so because of that we brought this the concept. Okay, so the reason I call this Dorothy, we're not in Kansas anymore, versus Cloud and Beyond, is because that's actually the first line from the AWS blog. It was actually literally called Dorothy, we are not in Kansas anymore. So what do we mean by that? So what are the lessons we learned from AWS? So, okay, actually, let me give you a quick primer, which I forgot to include. When AWS built what they did, there's a historical context. People thought that Amazon built AWS because what they thought was like, hey, I've got all this hardware that I'm buying for Black Friday sales, right? From Thanksgiving. And so because of that, we had to go ahead and, buy all this hardware. So now I've got this hardware just sitting here doing nothing. Okay, that's what a lot of people thought. Okay, and that myth keeps on going today. Okay, not at all true. It's a great story. Okay, but not at all true. The real reason they did it is because what they realized was that they needed to scale their hardware, and the infrastructure itself, scaling it, distributing it, was the hard problem. So they decided to standardize on web protocols, back to REST APIs, for everything. So you could standardize how you talk to it. When you built your microservices, we all agreed that this is the one format. It could even allow Windows to talk to Linux now. If you go back 15 years ago, like the war between Windows and Linux, Windows servers versus Linux servers, and trying to get a Linux server to talk to Windows server, it was laughable. It was pathetic, honestly, okay? Just like how we couldn't get a SQL server on Windows to talk to a Linux-based web server just because they were using different protocols, okay? Well, REST APIs, a la web standards, that changed all that. And now, of course, it's the default standard, okay? So that's actually why Amazon did it. They were just trying to figure out how to maintain their own infrastructure. And then they realized, hey, since we have this problem, maybe other people will have the problem. So they started selling the service. And guess what? Everybody bought in, and here we are today for all intents and purposes, okay? But then what's Netflix's lessons they learned from AWS, right? Because they themselves had to were early adopters of AWS, and they said, okay, well, what were their lessons? Well, you have to unlearn a lot of what they knew. So remember, I was talking about monolithic architectures, right? So they had to unlearn those monolithic architectures. So for you who are more used to microservices, when you're talking to data, you're going to need to go unlearn some of the problems of what you learn with microservices to realize the benefits of monolithic architecture in terms of data reliability now, right? In order to come back, okay? All right. for AWS, for Netflix and AWS specifically, it was basically about hardware reliability is not a constant. Like the cloud is doing a lot better now. Okay, so most of the time, really, the storage is up online, the database is online, all these things online. But if you build anything at scale, it's not reliable, right? You have to build in. Remember, I was talking about you have to design for failure. You actually basically had to build into your system this idea that the network connection is offline for 10 seconds. So your app should not die because of that. That's why you cache the movie or whatever else, right, in order to be able to compensate for that. All right. And so, like I said, you want to rethink about state. So I was just referring to one of the interviews that I had with EVP of Tableau, now part of Salesforce, Mark Nelson. In the MOOC, I was basically, he has a great explanation of exactly how a hard state really is, right? It's not an easy thing. So we alluded to that and talked a little about that in the beginning, but he dives even deeper into it, okay? This concept of co-tenancy is hard. Like, again, you're probably used to it because you're talking about containerization, Kubernetes, and all these other cool things. But the reality is that Kubernetes even itself is a hard thing to understand, because the whole point is that you're putting all these containers across, where in essence the operating system is across multiple nodes, not on my single Mac Mini here, or my iMac or whatever else, or my smartphone, right? It's distributed across multiple nodes, and then you have to have an orchestration layer that goes on top of it to maintain all the resources across all of these different nodes. Well, when Netflix had to do this on AWS, that didn't exist, by the way. Okay, Kubernetes was a later concept, right? It was based on our learnings for that. That's why we're able to create Kubernetes. That's before that we had to create containers first. And by the way, I know lots of companies make a big deal about containers, but containers are just like, they're just basically Linux systems. Okay, it's a packaging of the Linux kernel. It's not trying to knock containers. I'm just saying, it's because we actually had to design something right within Linux itself in order to be able to have the whole reason we have Windows containers right now is because Microsoft invested a lot of money into Docker to basically build it. That's actually the only reason why. Okay, but the context is, the third point is the most important point here. The system isn't trustworthy. Network failures. VMs are not spinning up, or they're taking too long. Non-ephemeral storage. Yes, you may not be used to this idea, but basically, even though you saved it to disk, if the VM was to collapse, that disk would go with it. And guess what? All your storage would go with it as well. Now, more and more VMs these days actually have ephemeral storage now. But even if they do, it's a best practice to store the data directly to like your blob storage, because that actually is replicated, right? So if your VM goes offline because the region goes offline, it's still sitting in blob storage that was replicated to some other region. Versus if it's sitting on your, even if it's ephemeral storage, sure, it's sitting on the disk that's on that VM that's associated, that's even specifically assigned to that VM. And by the way, that's usually suspect, but pretend it's even not suspect. Okay, how if the region goes offline? Doesn't matter. You don't have access to that data. So that's why we still tell you, you're gonna store it in blob storage for that purpose, because that data is now replicated to some other region, and you can always access the other region too. Okay. And the quote, best way to avoid failure is to fail constantly, right? I'm just going to jump to the last quote. When you're building services, no one cares if the system's patched. No one cares the system is working well. All they ever care about is if the system is down. Netflix is a great example. You don't care when your movie comes through in 4K beautifully on your iPhone. Well, it's not 4K, but still you get my drift, right? You don't care about that. You just care that when the movie isn't on it, right? That's all you care, because you're paying for Netflix as a service. So you care that Netflix doesn't matter that your 5G connection went from 5G to basically 3G. You care that they figured out a way to send it. Now, whether that happens or not is secondary, but that's what I mean by services. Like, they don't care about that. They only care if it's down or not. All right. Key important thing, and this is super important now when we're going back to engineering practices, test at scale. Okay. Everybody's very good at saying it works on my machine. And then I deploy it to production and the thing breaks because there's memory leaks out of hell, or because it's making assumptions about the storage authentication layer. I could go on for hours. I won't. But you need to test with real scale. Okay. You need to test in production. Okay. Now, key thing. Testing in production doesn't mean you're not going to test it before you go to production. And testing in production does not mean you're going to test production. Okay. In other words, you're not going to change the production database itself or the production data store itself. Because once you overwrite it and you overwrite it with the wrong thing, and if you don't have data versioning or data history, you just hosed yourself really badly. Testing in production means how you would normally run the system in production, you have to have a replicated system to do that. Now, what that implies is that you might actually have to have a replica of the data, replica of the same VMs, same infrastructure. Yes, you absolutely will do it. The great thing about cloud is that you can, provided you structured and organize yourself accordingly, you can use like for the Azure, you can build a template or whatever else. You spin up that entire environment, except it has a different namespace. So now it's on the test environment as opposed to the production environment. And then it runs through the exact same thing. You just store the data somewhere else. Okay. So this is what I mean by test in production. I do not mean, oh, let's go ahead and mess with the code that's currently running in production right now. That's not a good idea. Okay. And this bottom quote is actually my own quote, which is, often when you're trying to build things, you're trying to build for perfection, okay? You're trying to make it beautiful. You want the code to be beautiful. You want the architecture to be beautiful, okay? And what often works in really is ugly. Okay, let's be very clear. It does not look good. And I don't mean like, as in, like it was a bad design. Good design often can be ugly looking. Okay, let's be very clear, all right? So I'm not talking about design. Design has to be good, obviously, but the code may look ugly. The way you do a patch here may look ugly, but if it's easy to maintain and if it works, that's actually the correct judgment of if it's beautiful or not. Okay, and so that's a rigor that has to be built in, because often when you look at that's slightly different from data than software engineering, at least in the past. Though admittedly enough, when people who are building software engineering systems for distributed systems, they're rapidly understanding this concept. It's not supposed to be this beautiful, shining design, because your goal for perfection will result in you missing a whole part of the problem you're trying to do. And because you're missing that whole part, you can't actually easily update the system to handle it. And even if you had a perfect design now, a year from now, because of its success, where you have to change the model, you have to change the schema, you have to change whatever, you're going to make it look ugly again. So just accept it's going to be ugly anyways. And accept that the beauty is not the beauty of the code, it's the beauty of, because it's easy to maintain and it works well. That's what your judgment of beauty in data engineering, software engineering is supposed to be now, okay? And the final part, which actually leads also to the culture, commit yourself to doing it. Train, 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 train. You're going to make mistakes when you do these systems. Go through those mistakes. Make them. The biggest sign that I know my team is not going to do well is because they have a perfect track record. If you have a perfect track record, it's because either you didn't push yourself or you were a team that basically went ahead and changed the optics of the OKRs, of the metrics, to say, oh no, yeah, we really meant to only do 50 transactions per minute when you originally designed it to be 50,000 transactions per second, right? So no, I can guarantee you, any good team, any great team, any software engineer team that knows how, they were going to make millions of mistakes, and that's a great thing, okay? And so you start with small projects and small teams, and then expand accordingly, okay? And you have to have the grit and conviction to fight. And so before I go into culture, I want to tell you this other story, which is, for example, when I was at Concur and we had to make that shift from monolithic architectures to microservices. We had backing not just from our engineering team, right? I was part of the CTO organization, so we already had the CTO backing, right? Since I was one of the guys who actually had to push it. We had backing from the business. We had backing from the CEO. We had backing from the COO. What do I mean by backing? I mean, we would take entire engineering teams offline for 2 weeks at a time so we could train. So we could get every single person that had, like, for example, a database experience, and now we're trying to teach them how to do microservices. We actually would train them on this stuff. We didn't train them on new technology yet. We trained them on process first. So all we were trying to do is we're trying to train them on agile development, about delivering things faster. We weren't even trying to change, like, stop using databases first. We were literally just trying to change them, go from waterfall method into agile development. That's actually all we were trying to do. And that took us 6 months, okay? Our business team was so into backing us up on this because they recognized that they could get their deliverables faster if the engineering team could go ahead and switch to this agile model, that they themselves changed all of their business processes to be agile development too. So they were sitting in us with us training. So we had the CEO, COO, CTO, all in complete alignment. When I was pushing for, like, for example, to do these type of techs and this type of projects, the VP that I was working closely with, he was going ahead and pushing for, here's the money to train everybody. And then we went ahead and converted teams, not over months, it took us 2 years. But because what happened nicely was that we actually wanted to make it very clear, we were going to invest in every single employee of Concur. You had built up your entire career on monolithic architectures. Now we need you to switch to microservices. And we're going to invest the time to help you learn. So you've got 2 years to figure it out. If you still have 2 years, you might want to leave. But we gave you a 2-year warning to do this. And we're going to put money and resources behind to train you to do this. Right? And so you notice that after the culmination of all these processes, it goes into the people, that we actually showed that we cared about our people and we did everything we could. And so the one little note that I want to call before I go into the culture part is that there's one friend of mine that I interviewed also for the overall MOOC, where he originally was a Java developer. Okay, so he built a monolithic architecture on Java over Java. And basically, this particular software package was basically convoluted, massively large. Dear God, how many Java files there were, how many classes there were. It was ridiculous. Okay, it was painful to read. Okay, and there's me, the data engineer. Like I obviously had software engineering practice, but I was definitely still coming from a data perspective, especially a big data perspective. In the interview between him and me, what was interesting is that after 6 years of not working together, but we were progressing, we basically realized that even though I came from a data engineering perspective, and even though he came from a Java software engineering perspective, we're basically both doing the same thing now. That's what I mean by that convergence of software engineering and data engineering. So we all agree. We agree that microservices is the route. We agree that there's times where monolithic architecture makes sense, but it's because, and we came in from very different angles, but we actually both came to the exact same conclusion, came to the midway. And so that part where I say database, Uber microservices, that's Tasso microservices, that database, that's me using the most extreme version of each other. We weren't that bad, obviously, otherwise we wouldn't get along well. Like I said, when it comes to software engineering, we have to go somewhere in the middle. Him and me are actual examples of exactly that we're both coming to the center because we realize the benefits of both sides. We realize the benefits of microservices, yet also of the veracity of your data, the data reliability aspect of things, okay? And so finally, about culture, and this last 2 stories is really about that, of my version of this thing, okay? This link that is called Network Culture, Freedom, Responsibility. It is the best 120-page PowerPoint slide deck I've ever read in my life. What I said is basically wrong, okay? You should never enjoy reading 120 pages of a PowerPoint deck. That's ridiculous, okay? And it didn't even have any graphics. It was just black text on white. That's it. I'm a little bit better, not much, if you'll notice with my slides. Okay. But the reason I think it's worthwhile for you to look at it was because it's this concept of how you change your people to fit in this world of software engineering practices in this way, right? That you ultimately need to have them shift these people to microservices. This is the story that I was talking about Concur, how we had, in essence, a 2-year plan to shift people over. You got to train your teams. You got to be patient. Some will thrive and some will not. Remember that. Some will do well in this environment. Some will not. And that's okay. You have to understand some people are still going to be stuck in, for example, that monolithic architecture database world. And there'll still be jobs for them, just not jobs in this company. That's okay. Don't keep on an employee that wants to do database architecture when you're already on microservices, because guess what? They're not going to succeed and your company's not going to succeed. Your project's not going to succeed. So make you do that. And here's the other part, which is sort of pretty closely near the end. When it comes to culture, right? No culture satisfies everybody. Okay, and that's exactly the whole point, right? We can talk about, like, Asian cultures versus American cultures and all these other things too, but but the fact is, like, somebody like myself, I can fit well in both because I'm an ABC, so I'm Asian, but I bother to learn Mandarin, though I don't want to speak it right now because then you'll laugh at me. But the whole point is that, like, I can do that dichotomy, but even then, that's not completely true. I'm not truly Asian and I'm not truly American either because of it. Okay, so that's more or less that point. Like, this is just me talking from a personal perspective, but no culture satisfies everybody. Cultures are meant to keep, find, and reward people who are in that group. Now, I'm not trying to be, that's more or less the point. When you build a software engineering practice, you end up building a culture whether you mean it or not. Some cultures are much more academically based. Some are more agile, deliver, and I don't care about the quality. What you're hopefully trying to do is trying to do somewhere in the middle, which is you have enough academics so you can think about the problem. You have enough people who are trying to deliver fast so they actually can go deliver, and you meet somewhere in the middle, right? You notice how everything's about meeting somewhere in the middle always, right? And that's more or less the point, right? When you build up a team, when you talk about software engineering practices, one of the key aspects that's often forgotten, yet is the most important thing, is the people behind it. And this is applicable to everything, the data, to software by itself. It's applicable to everything. But the reason I always bring this up when it comes to data reliability, okay, is because, number one, software engineering and data engineering are, even though there's a lot of parallels, there's still differences. Right, so data engineering in itself has its own culture, just like if you're a Python developer, has its own culture. Just like if you're a PHP developer, you have the PHP fans, or the JavaScript folks, right? Like, in essence, there's a culture for these different modes of computer engineering. Data engineering has its own, right? And because of that reliability aspect is crucial to that data engineering culture if you're to succeed. And the other thing about reliability, which people forget, is the people who are actually writing the code behind it, people who are maintaining the data behind it. The people who are there, how you're reliable is because not only the process you create, but because the people who actually wrote the code in the first place, the team that makes it up. So that's why I always end, like, one of my conversations into this, because in the end, unless you have that full picture about the differences between data and software, about microservices versus monolith, and the people and the culture that you have to shift, whether it's because they're 2 microservices and they have to now understand data reliability, or they're 2 databases and they have to understand microservices, this is crucial for you to finally basically deliver what you need to deliver. Okay, so final key themes here, just to end it. Use the right tool for the right job. Microservices and learnings from the monolithic architectures. that convergence of data engineering and software engineering and culture is important. Okay, so yes, okay, I still have 15 minutes left, so at least I didn't make you guys stay longer, so that's good. Any questions? I'm sure I threw a lot of stuff at you, so I apologize for doing too much, but there you go.
Thank you, Danny. Great stuff. I mean, there's so many things to think about, but let's see if the students have any questions, guys. You can speak up or you can just write it on the chat.
Cool. I know it's a chat question here, so let me start with that one. I've emphasized a lot about having rigor in data engineering practices. How do we start applying this rigor as students doing student projects with very tight deadlines? Yeah. In fact, that's exactly the point. Everything you do when it comes to software and data engineering is tight deadlines. There's no Google, even with all the money they have, it's not like they don't have tight deadlines. Everybody has tight deadlines. Like it doesn't exist. That's why you're paid the big bucks, okay? when you get out, right? Because you have these tight deadlines. In terms of practice, the key thing is it's less, where you're gonna see in action is less about how you deliver your own project yourself and more about how you deliver projects with multiple people. But let me break those two things down. How you do it yourself is that you actually document things well. Okay, that you know where the data lineage is. You know where you're getting the data from. You've documented it out. It could be something as simple as a quick comment in GitHub, if all I care, right? But the point is that you have that. And the reason why that's important is that you will, as a software engineer, as a data engineer, as you progress, you're going to forget everything you did. I guarantee you, okay? Stack Overflow and Google will become your best friends, okay? Like the running joke I have is like, they show you an engineer type, like writing the code super fast on a keyboard. First of all, it's usually a crappy keyboard, but anyways, they just magically know the code, and they say that's real. I'm like, no, the real is that they went to Stack Overflow and copied some code and pasted it out, and then they wrote it down, or they Googled it. That's what real is, okay? So because of that, you're gonna forget everything you did. So that's actually why attribution is so important. So when you do, for example, GitHub comments, you say where the data is from or where the code's from, in the code, that's why you often will say, hey, in my code itself, I will go ahead and comment and say, I got this idea from here. Right? Just simple things like that, right? Because that's what rigor is, right? It's that you've decided whatever process it is you do, okay? That whether it's an agile model, you pair test with somebody else or whatever else, that you've documented everything and you follow process, whether it's Jira, GitHub, whatever, you've actually bothered using those tools. That means it takes time. Key thing, it takes time for you to build a rigor. You're going to check, you're going to document what you do. The Apache Spark project is a wonderful example of how this can work really well. Okay, the reason why the Apache Spark project is actually as good as it is because it truly is multiple people working on the project at once. There is not one single person that maintains it. And the reason why is because we actually use GitHub and Jira extensively so we can debate, comment, document everything. Every single thing about it, pro and cons, rights, wrong, negative, pluses. We put it all down. Even if we decide that we don't care about that problem for now, guess what we do? We document the fact we didn't care about it. That we're not working on this problem right now. So that way it's known that we made a choice to not deal with this. And when later on it comes to bite us in the butt for doing that, oh yeah. But at least there's all these comments that says, here's how to fix it. Because you bothered documenting it all, right? So having that rigor, so I'm older, right? And I've been doing this for a while. To give you an idea, part of it's probably just loss of brain knowledge because I've drank too much or whatever else. More times than not, I've designed software, I've written data code, then I'll school. I'm like, what? I don't remember how to do this anymore. I Google something and sure enough, I find my own code. I'm like, oh crap. That happens to any experienced software engineer, data engineer. You will hit that problem over and over and over again. personally, the whole reason I wrote a blog, I have my own personal blog, dennylee.com, okay? I haven't updated in a while, so I'm not trying to promote it, but I'm just gonna say I have it, is because literally, and I'm not joking at all when I say this, is because that way I could write down, it wasn't so much that I wanted to advertise what I did, it's so much that I could write down what I did so I would remember it. So when a month and a half later, I don't remember what I did, I just do a Google search, find it on my blog, and there you go. I can go and do this all over again. You can do the same thing with GitHub. You can do the same thing with whatever else. It doesn't matter. You choose how you want to do the flow. But the point is version. So whatever it is you do, you're going to need to make time for that. Okay. And it sucks because you think to yourself, but I barely have enough time to get this project out. True. But what happens is that if you don't have the rigor, you're going to forget. And that means it's going to take even longer for you to deliver it. And that forget could literally be a week later. This isn't like a month, year where I'm making jokes about my memory. I'm like going, I figured it out. I did it. I wrote it down. I wrote the code down. 3 days later, 1 day later. What did I write this for? I don't remember what this does. Just because you didn't comment the code. Just because you didn't go ahead and put explain in the lineage of where you got the data from. Okay, so this rigor is actually crucial for you, and you practice it now. You practice it when you have tight deadlines, because you want that to be a mental model. You want that to be trained into your system. That's default. That I always have tons of comments, whether it's the code I'm writing to the notebooks that I'm writing. Just because I will now always make the assumption I forgot everything an hour from now. Because more likely than not, that's true. So I hope that helps provide you a little context there.
Thank you. It's really illuminating.
Cool. Kenny's asked a cool question. Besides adopting framework architecture that support veracity testing and scale testing at the production staging environment, do you have any other advice to ensure the quality of the software and data engineering project? Honestly, that goes back to my part about people, right? Because the reality is there isn't a single coding language that's better than the other, right? Here's the best way I can describe it. If I've got a bunch of people who write Python code beautifully, but then I tell them to go write the stuff in Java, doesn't matter that they're best Python developers in the world, they're not going to write the code for me. It would be better to basically bring in a half decent Java developer, work with the Python developers in terms of architecture, and then have the Java developer write it, than it is for me to go ahead and make the Python developers go write the Java code, right? That's an oversimplification, but that's basically the idea, right? So that's what I meant by the training aspect, right? So when you say adopting a framework or architecture, the fact is framework and architectures change, right? Like it was monolithic, just for data, it was monolithic before microservices today. For example, the running joke that I usually say is like, yeah, and once quantum computing comes in, our entire architecture is going to change again anyways, right? So I'm not waiting, when I'm saying quantum computing, I'm not joking. I'm saying I'm not waiting like if it's going to happen. I'm literally waiting, when is this going to happen, right? It's going to happen within our lifetimes here, guys, right? This change. There's a very good potential chance that genomic data encoding, in terms of storing data in cellular genomic systems, is actually going to be within our lifetime too, right? So how we read data from genomic systems, how we do computing quantum systems is going to be a whole different ballgame. So yes, it doesn't mean you don't want to adopt an architecture or framework. You absolutely want to adopt an architecture and framework that's well known. It's not just popular, but as in well known, as in the community supports it, right? So you can ask questions from each other. It's not just about asking questions in the company that you're in, but asking questions in the community. Obviously don't share any secrets of your company, but yeah, you can ask questions with the community. Well, that's why Spark is the de facto big data platform right now, because it wasn't just about great tech. It wasn't just about great design. It wasn't just about all these lots of committers from lots of different companies working in it. So that we have a very avid community that helps each other out, right? This is crucial, right? But then there's also that aspect of, like, testing, production, veracity, all these other things. All these things will change over time. So because these things potentially change over time, that's why I'm saying, in the end, ultimately about the quality of the software and data engineering project, it is about your people. It's about ensuring that they have enough technical competence to be able to do their thing, but then actually providing the support and the culture so that they can always learn. They can always learn the new thing, because that's the thing about, like, about software engineering, about data engineering. You're always going to get new data. You're always going to have new software frameworks. So unless you have people that are willing to learn how to deal with data in a different way, how to understand a new software framework, you're not going to have a successful team. So just to provide you some context in terms of team hiring, the people that are really good at this one thing, which is a solid, Scala developer, but they don't want to learn, they're contractors. You hire them in to do a job. They do the Scala code really well, and then they're done. The person that is a solid Python developer, but willing to learn C++, willing to learn machine learning, willing to learn that's your teammate. That's the person you want in your software and data engineering team, because they're going to learn, because when the data changes and they have to now try a different framework, right? The data engineer is the person that says, I went ahead and build up the system that did Kafka topics to get all the data into Kafka to structured streaming. So now I have a real-time system that's processing data. And then all of a sudden it says, okay, now we need to start learning how to do machine learning to run Python against in a distributed manner using Pandas UDFs or Python UDFs against all that data we just stored in Spark for that. Boom, that's the person we want, because now they've adapted to the new system. Okay, so that's why I talk so much about culture and people, because ultimately these are the people that make it successful. Right? It's not a framework that makes it successful. It's basically that mode of thinking, that mode of willingness to learn new things. That's what makes these projects always successful. That's why so few projects succeed. Right? That's why only 15%, depending on how you count it, 15 to 35% of the projects succeed. Because it's there's not all people are those people. Not all people are the ones that can go ahead and adapt to changes like that. Okay.
All right. Thank you, Danny. Thanks for very detailed explanation to this question. I think, could you take another one?
Of course.
Please, yes.
Okay. Listen, what kind of organizational processes do you use in enterprise when deciding right tool for the right job? It's about cost, resilience, compliance. Okay, and then just a great example. Like if you dump all your small images files into S3, you're gonna rack up a lot of put requests. Yeah, absolutely. Well, oh, by the way, no, it's actually less the put request is more the get request when you're trying to get it out of the system. Amazon's makes it super cheap for you to put data into it. They make it really expensive when you take it out of it. That's actually where the real cost is. But nevertheless, your context is completely right. And the fact is, that's why DevOps is itself popular, because your developer actually needs to understand this concept of get put request and the associated costs with it. That developer now, she also has to go ahead and be able to debate with other people on their team on the pros and cons of each approach. And that other developer that's working on the team, he or she needs to go ahead and be able to debate why this one makes sense. And what it boils down to from an organizational process is that to oversimplify it, it's this: you have to have an organization that is resilient to failures. i.e., you have management support to fail. And the reason why that's so crucial is because that's the only way your team is ever going to learn. And once your team learns, they're going to fail less, true. But they have to be allowed to debate, because there's no one right answer to this question, right? Maybe using MongoDB was a really bad idea before. But for this particular project, it's a great idea, because you bothered to debate and document why you made the choice to not use MongoDB in the past, but why you do still like it. But even though you chose why you don't, for the first project, you chose not to use it. Well, because you wrote everything down, you go back to your notes and you realize, oh, okay, it was crappy for project A, but it's really a good idea for project B for those reasons, right? Because every single software project you have, every single data engineering project you have, right? If you really dig into it, you realize that there's going to be pros and cons to every single approach to it. And so your job isn't to say that there's the perfect technology or perfect technique or perfect whatever. It's to say, how much of this particular tech or this particular framework or this particular whatever covers what I need to do. So it's the old 80-20 rule, right? So that way I only need to do a little bit of work to compensate for what it can't do. Every single piece of software, every single data system will have problems. Does your team have the skill set, knowledge to basically cover up for the 20% that the tech you chose doesn't do? And that's how you make that choice. And so that's ultimately the organizational process, the ability to debate, the ability to have independent thinking, right? That's why we talk about agile teams, right? And the reality is, you know, and Chester, I'm going to go really long into this. I'm going to definitely shrink it down. It impacts everything, right? Because maybe this time cost, I'm trying to make it as cheap as possible, but the next time it's like, yeah, maybe I'm going to pay the S3 get, but I just saved 6 months of development time, so it's worth it, right? Or when you talk about resilience, you have to categorize your data. Some of your data, like I said, like using the Facebook messages or Facebook like context, I have to have resilience from the standpoint that it's consistent. I can't go ahead, have one note said I liked it and another note say I didn't like it. I need it to be consistent, right? If you like are reviewing my Facebook, you know, likes, and you're logged into node 128 and I'm logged and I'm putting the like in node 2. Node 2 and node 128 sure as hell better have that like, right? To be consistent. But if it's consistent at the risk of being unavailable, fine. Now node 128 simply doesn't show the like because it can't be consistent with node 2, right? This goes into Raft, Paxos, and all those consensus protocols. Again, that's a whole other can of worms. But the context behind me calling this out is because you have to know what state your data really needs to be in, right? So in some cases, resilience absolutely is 1000% required. In some cases, it just plainly isn't. And your application, in fact, more times than not, it's more than one thing. This part needs to be consistent. This part's more important to be available. This part, I actually have consistency availability. I don't care about partition tolerance, right? So knowing that context of resilience is super important. So you're going to have to break it down. And then finally, compliance. Compliance is a massive can of worms, right? Because data versioning comes into play. Be able to do GDPR or CCPA or whatever else, all the different governance, risk, and compliance context that you have to go with it. Every single data company is going to suffer from this one way or another. Build it right from the beginning. Understand the difference between security and privacy. These are two different concepts. Understand the difference between authorization and authentication. Understand all those different things. You don't have to be a security engineer Okay, I'm not claiming you have to be one, but guess what? As a developer, you sure as heck better respect it, because the data that you have needs to be protected. The time that you decide that that data is an important, that the protection of your company is $1 billion. Hope that helps.
Great. Thank you so much, Danny, again for another very detailed explanation, like drawn from the experience as well. So it's very helpful for us too. I think unfortunately we're running out of time, not only because it's very late for Danny there, but also some of the students here have to run for another class. But
I figured as much.
yes. So again, we really appreciate the talk today, Danny. And if you come to Singapore again, please give us a shout. Okay.
Absolutely. I would
Right.
definitely consider it done. All right.
Okay, cool. All right. Thank you, Danny. Thanks for the talk. I will upload it and then send you the link.
Perfect. Hey,
Yeah.
thank you very much for inviting me. I really appreciate the time.
Thank you. Bye.
All right. Take care.